Hello, and welcome to this video on convergence of a series by using the integral test. So we have the series from 1 to infinity of 1 over n to the p, and p is a number. We want to know for which values the series is convergent. So let's see. We have various things to do here. So notice that the nth term of the series is a sub n equals 1 over n to the p. And p can be positive, negative, or 0. If p is positive, then notice that 1 over n to the p gets really small as n goes to infinity, because then we're doing 1 over something huge to a positive power. In the case p is positive, we have a 0 in the limit. For instance, p is 2, p is 3, 1 over n cubed, 1 over n squared, they all go to 0 as n goes to infinity. But if p is equal to 0, then we have 1 over n to the 0, and n to the 0 is 1, any n. So if p is equal to 0, then the limit of an is actually 1. While if p is negative, for instance, p is equal to -1, we have 1 over n to the -1, and that's the same as n. When we take n to the top, we change the sign of the power. The -1 turns into a 1. We get n, and notice that this n goes to infinity as n goes to infinity. And if we had any other negative power, whatever power negative q, 1 over n to the negative q is just n to the q on top, where q is positive, and that goes to infinity as n goes to infinity. You get infinity for p less than 0. Then from that limit that we just found, we can say that the series does not converge for p0 or negative. And that's by the nth term test. When we have the addends we're taking are not going to 0 as n goes to infinity, then we can definitely say that the series is not going to converge. That test is also called by the divergence test. Okay. So from now on, suppose that p is positive. Let's see what happens when p is positive. When p is positive, the limit of an is 0. We saw that. Now, we're going to match an with f of n, where f of x is 1 over x to the p. When we do an, that's 1 over n to the p, that's the same as f of n. And this function f that we have here is a function that is very nice as long as we stay away from 0. And we are staying away from 0 because we're starting with n equals 1. So the function we have is nice, and what we mean by nice is continuous. It's also positive as long as x is positive. And the function is decreasing. We have something that goes down. Decreasing as long as we keep two numbers after 1. So we can say that this function is very nice. It's positive and decreasing from 1 to infinity. And then when we can match an with f of n, where f is a function like that, we can use what is called the integral test to test for convergence. So by the integral test, what we have is the following. So the integral test tells us the following. The summation from 1 to infinity of 1 over n of the p gives us something convergent if and only if the integral from 1 to infinity of the function f of x we took converges. That's what the integral test tells us. Whenever we can match an with f of n, where f is continuous, decreasing, and positive from 1 to infinity, the series of that looks like a summation from 1 to infinity of an converges if and only if the integral from 1 to infinity of the function converges. And let's write the function more explicitly. We have 1 over x to the p. So at this point, all we have to do is we have to check the integral from 1 to infinity of 1 over x to the p. And we need to see if that integral converges or not. The values of p that give a convergent integral are the values of p we're interested in. Now, the integral from 1 to infinity of 1 over x to the p is the same as the limit as b goes to infinity of the integral from 1 to b of 1 over x to the p by definition. We define improper integrals like the one we have by using limits. We have the limit as b goes to infinity of, then we can rewrite 1 over x to the p as x to the negative p. Okay. Now, if p is equal to 1, then the integral from 1 to b of x to the negative p is written in terms of a ln. Well, actually, yeah, it's just one ln. We will see that. Because then we have the ln of the absolute value of b minus the ln of 1. And that's the ln of b because b is positive. And then the limit as b goes to infinity of the integral from 1 to b of x to the negative p is infinity because when we take an argument that is really large, ln becomes really large. So we have that the integral diverges in the case b equals 1. Then integral diverges for p equals 1. Now, if p is different from 1, what we can say is that the integral from 1 to b of x to the negative p can be found by using the power rule for integrals. Have negative p plus 1 over negative p plus 1. And then we evaluate that at 2 separate points. One of them is b, the other one is 1. So we get 1 over minus p plus 1, and then b to the negative p plus 1 minus 1 to the negative p plus 1. We're substituting b and 1 into the antiderivative we're using by the fundamental theorem of calculus. We have 1 over negative p plus 1 b to the negative p plus 1 minus 1, because 1 raised to any power gives us 1. So then we're saying that the integral from 1 to infinity of 1 over x to the p is the limit as b goes to infinity of 1 over negative p plus 1 times b to the negative p plus 1 minus 1. And let's write that on a separate page. There you go. There we have that. And what we can say that here at this point is that when b is huge, and remember b is different from 1, so here we don't have minus 1 plus 1, it's just minus p plus 1. P can be any positive number different from 1. When b is huge, this term is going to go either to infinity or to 0, depending on the sign of negative p plus 1. If negative p plus 1 is positive, like say 1 or 2 or any other power, then we have that b to the negative p plus 1 goes to infinity as b goes to infinity. While if the power on b is negative, then we're sending b to the bottom. And then in that case, we have that b to the negative p plus 1 goes to 0 as b goes to infinity. Then the integral from 1 to infinity of 1 over x to the p for p different than 1, different from 1, is either infinity, that's in the case negative p plus 1 is positive, or something else, that is 1 over negative p plus 1 times 0 minus 1. That's in the case we have negative p plus 1 negative. And notice that 1 over negative p plus 1 is positive when negative p plus 1 is positive. So we stay at infinity when we go with p negative p plus 1 positive. So what we can say here is that the integral converges for values of p that satisfy this inequality, and only for those ones. And that's for values of p that satisfy 1 less than p or p greater than 1. So as a result, the integral from 1 to infinity of 1 over x to the p dx converges if and only if p is greater than 1. We have convergence of that integral if and only if p is greater than 1. Notice that we checked p equals 1 separately. We saw that the integral diverged for p equals 1. Then, by the integral test, what we can say is that the summation of numbers 1 over n of the p gives us something finite if and only if p is strictly greater than 1. Okay, so we can summarize this problem in the following way. We are given the summation of 1 over n to the p, and n goes from 1 to infinity. P can be anything, positive, negative, 0. So the first thing we did was we analyzed what happened with an as n goes to infinity. An is the nth term of the series, 1 over n to the p. We can already tell that when p is negative or 0, 1 over n to the p doesn't go to 0. Then in that case, the series doesn't converge by the divergence test, or the test of the nth term of the series. Now, from then on, we supposed that P is positive. We analyzed P positive in greater detail, and we saw that we said that f equals 1 over x to the p is continuous, positive, and decreasing from 1 to infinity. Then we use the integral test to say, okay, then our series converges if and only if the integral from 1 to infinity of 1 over x to the p converges. Having convergence of our series is the same as having convergence of that integral. So we analyzed the convergence of the integral separately, and we found that only that we have convergence of the integral for p greater than 1 only. Then we said, okay, then our series converges for p greater than 1 only. Right, this is a long problem. I know you have questions. If you have questions, and it's very likely you do, then write comments, and I will be glad to help you or try to address those questions. Please watch the video various times. I know this takes a little bit of time to kick in, but the ideas are all there. Right. Thank you for watching. Bye-bye.